David Reber, Empa, Switzerland.
In light of the energy transition, more renewables are installed every year, which is great, but due to their intermittent nature, there's a mismatch between production and demand. And as we're all creatures of habit, we will not be able to simply adjust our lifestyles to this imbalance. Therefore, energy storage is needed to shift the loads on the grid. What about large batteries? In the developed world, lithium-ion batteries are conquering the market due to the large amount of energy they can store, but they are expensive and contain critical cobalt and lithium, as well as electrolytes, the liquid between the two holes of the battery, which can leak and are as flammable as the fuel we use to melt the cheese for our fondue. The most common non-flammable alternatives are based on water. These are cheap lead-acid batteries commonly employed in the developing world. We want to combine the best of both worlds because also these contain sulfuric acid and carcinogenic lead, and we want to develop an aqueous electrolyte which is non-flammable, non-toxic, and non-corrosive. But there's a problem. Neutral aqueous electrolytes only allow cell voltages of about 1.5 volts, so you have low energy density. And we now developed a highly concentrated salt solution that's 8 grams of salt in 1 gram of water, which allows cell voltages of up to 2.7 volts. Using only abundant materials, no cobalt and sodium instead of lithium, we implemented this electrolyte into a safe and green lab-scale battery, and it works. It's stable over hundreds of charge-discharge cycles with the highest energy density reported to date for an aqueous sodium-ion battery. So why should you care? Ensuring safe operation is of highest importance for large-scale installations where shipment container-sized batteries are needed, or home appliances such as the Tesla Powerwall. We all heard of malfunctioning mobile phone batteries. In a phone, that's one thing. In a shipment container, that's another thing. And following our approach, both the cost and ecological footprint of such large-scale systems can be drastically reduced while maintaining unparalleled levels of safety. It's impossible to burn these things. We believe that by further improvement of the general concept, we can still push the maximum cell voltage possible and eventually compete with flammable lithium-ion batteries. That would be breaking the wall of large-scale energy storage. Thank you.
So what salts do you use in your batteries?
We use something called sodium FSI, so that's a bit of an exotic fluorinated sulfonamide, but we're working on ways to use acetates as well, so easier salts.
Do you have a cost model?
Sorry?
Do you have a cost model?
Not yet. I'm more in the lab, but hopefully someday.
Over there.
Can you make this all solid state?
My colleagues are working on solid-state batteries. I'm stuck with the liquid systems, which is a good thing too.
Fabulous. Thank you very much.